if I have basically a product of two numbers in here, I can break these numbers up and multiply them individually. Same thing with the quotient. I could have A and B under the radical sign, and I can change it to just the radical of A divided by the radical of B. When multiplying two radicals, you multiply the number for each of them, whether it's a square, a cube. Okay, so with a radical, if I have A raised to some number, if n is odd, then the answer is just going to be a positive A. If A is raised to some number, and n is even, it equals its absolute value. And then finally, A raised to the let's go with if I have the cube root, let's do this one here. So A, the n root of A, all raised to the m, can be written as a fraction over here, an exponential. And it can also be written like this too. So there's three ways to write a radical. A complex number is an expression of the form A plus BI. So a complex number is an expression of the form A plus BI. Where A and B are real numbers and I squared is equal to -1. The real number, or the real part of the complex number, is A, and the imaginary part is B. Two complex numbers are equal if and only if their parts are equal and their imaginary parts are equal. Okay, so with exponents, if I'm multiplying two exponents, like x squared times x squared, I just keep the exponent and then I add, I keep the base and then I add the top numbers. And the same thing if I have a quotient when I'm dealing with exponents, I keep the base and then I subtract the exponents. And the biggest number is always where the exponent will be. So when I'm multiplying two exponents, I keep the base and then add the exponents, the superscript. When I'm dividing two exponents, I keep the base and I subtract the two exponents. So if I have some value, a to the m and then all raised to the n, I can multiply that m and n together. And on the same token, I could separate them too. So if I have a quotient of a negative fraction with an exponent, I can just flip it. The quadratic equation, the general form for a polynomial is ax squared plus bx plus c equals 0. Now the quadratic formula is used for finding zeros of harder polynomials. The discriminant formula of the general quadratic equation is ax squared plus bx plus c. Okay, so when I just take the b squared minus 4ac, and I solve for it, if d is greater than 0, then the equation has two distinct real solutions. If d is equal to 0, then the equation has exactly one solution. If d is less than 0, then the equation has no real solution. 180 degrees equals pi. 1 radian equals 180 over pi. 1 degree equals pi over 180. To convert to pi, you multiply pi over 180 divided by 1 over pi. To convert the radians to degrees, you multiply pi over 180 divided by pi over 1. Power reduction formulas for sine squared, cosine squared, and tan squared. Sine squared equals 1 minus cosine 2 squared divided by a 2. Cosine squared equals 1 plus cosine 2x divided by 2. Sine squared power reduction equals 1 minus cosine 2x divided by 2. Cosine squared is 1 plus cosine 2x divided by 2. Tan squared is 1 minus cosine 2x divided by 1 plus cosine 2x. Double angle identities. 2 sine x equals 2 sine x, or 2 sine cosine x. Double angle identities. 2 sine x equals 2 sine cosine. Cosine 2x is equal to cosine squared minus sine squared. It can also be 2 cosine squared minus 1, or 1 minus sine squared. Tan 2x equals 2 tan divided by 1 minus tangent squared. Double angle identities. Sine 2x equals 2 sine cosine. Cosine 2x equals cosine squared minus sine squared. It also equals 2 cosine squared x minus 1 and 1 minus 2 sine squared. Tangent 2x equals 2 tan divided by 1 minus tan squared. Half angle identities. For sine x over 2 equals the square root of 1 minus cosine x divided by 2, plus or minus the square root. Cosine of x over 2 equals plus or minus the square root of 1 plus cosine x divided by 2. Sine x over 2 equals plus or minus the square root of 1 minus cosine x divided by 2. Cosine of x over 2 equals plus or minus the square root of 1 plus cosine x over 2. Tangent x over 2 equals 1 minus cosine divided by sine, or it can be sine divided by 1 minus cosine u. The area of a triangle is 1.5 a times b, or base and area, or a times b on the triangle, times sine theta. So the area of a triangle is going to be area equals 1/2 times AB in the triangle times sine.
Why don't you take them?
The reciprocal of secant is 1 over cosine. The reciprocal of sine is cosecant. The reciprocal of tan is cotangent. Pythagorean identities: sine squared plus cosine squared equals 1. 1 plus tangent squared equals secant squared. 1 plus cotangent squared equals cosecant squared. Even and odd functions. Sine of negative x equals negative sine of x. Cosine of negative x equals cosine x. Tangent of negative x equals negative tangent x. The law of sines. Sine A over B, the law of sines is sine big A over A, which equals sine big B over little b, equals sine C, big C over C. So we're just going to say sine A over A equals sine B over B, which equals sine C over C, where the top letters are angles and the bottom are numbers. Law of cosines. A squared equals B squared plus C squared minus 2B C cosine A. So the law of cosines, we have A squared equals B squared plus C squared minus 2BC cosine A. We also have B squared equals A squared plus C squared minus 2AC cosine B. And finally, we have C squared equals A squared plus B squared minus 2AB cosine C. Okay, so we have 0, 30, 45, 60, and 90 on the unit circle. 30 degrees is pi over 6. And its coordinates is square root 3 over 2 cosine and 1/2 for sine. 45 degrees is pi over 4. And the point is square root 2 over 2, comma, square root 2 over 2. Pi over 3 is 60 degrees. And its coordinates are cosine 1/2, comma, square root 3 over 2. Okay, so 30 degrees is pi over 6. The coordinates are square root 3 over 2, comma, 1/2. Pi over 4, or 45 degrees, is square root 2 over 2, and square root 2 over 2. Pi over 3, or 60 degrees, is 1/2, square root 3 over 2. So we have 0, 30 degrees is pi over 6. Square root 3 over 2, comma 1/2. 45 degrees is square root 2 over 2, comma square root 2 over 2. 60 degrees is pi over 3, and that's 1/2 square root 3 over 2. Sine of arc cosine equals 1 minus x squared. The sine of arc tangent equals 1 divided by the square root of 1 plus x squared. The cosine of arc sine equals 1 minus x squared. The square root of 1 minus x squared. So at 30 degrees, sine is 1/2, cosine is square root 3 over 2. At 45 degrees, cosine is square root 2 over 2, sine is square root 2 over 2. At 60 degrees, cosine is 1/2, and sine is square root 3 over 2. So we look up here, and there are different notations, but they all mean the same. It's good to know them when you're reading math texts and physics texts, as they're typically different. The x dot notation is known as the Newton dot notation. This notation is used when we're talking about time. So f prime of x is basically the derivative of that function of the derivative. So the definition of the derivative is f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x divided by h. For the formula for, if we're talking about the derivative of two functions, you can take the derivative of two functions and you can add them together. So the derivative of a constant function is basically the constant, which is then times whatever the derivative is. So, and the derivative of a constant itself is just 0. The mean value theorem is an important tool we can use in calculus. The mean value theorem states if there exists a point C on some interval, we'll call the interval AB. And so this means that between the interval AB, there's a C. If that's true, there's a tangent line parallel to that line passing through the point A, f of A, and B, f of B. The intermediate value theorem states that if f is a real value continuous function on an interval, so we got from A to B, and in the middle there's C, then somewhere along the way there should be a tangent line. Okay, so the product rule for the derivatives is f prime g plus fg prime. The quotient rule for derivatives is f prime g minus fg prime divided by g squared. The chain rule says we take the derivative of the outside function times the inside function. So the limit as x goes to infinity of some value c over x raised to the r is going to be 0. And that makes sense because we keep plugging in values for r, larger values, as this function is going to get smaller and smaller. L'Hopital's rule. L'Hopital's rule allows us to use the derivative to evaluate limits involving indeterminate forms. So if I had a limit and I had a quotient, and on top, if I had to manipulate that, the two limits, and they become an indeterminate form, I can take the derivative of both of the top and the bottom singly, and then I can find the limit. Okay, so the limit with a constant multiple is just going to be the limit, whatever that function is, times the constant. The limit of two functions, I could take the limit of both functions and add them together. So the product of a limit of two functions is basically the limit as x approaches a of f of x times the limit as x approaches a of g of x. Same thing with division. You can take the limit of the top of the function divided by the limit of the bottom, and you can still find the limit of the quotient, barring that the bottom doesn't equal 0. Okay, so for Power's rule, on the limit as x goes to a of some power, basically means, take the limit, raise whatever power it is, and that's going to be the limit. The limit of e dx as x goes to infinity is infinity. The limit as x goes to negative infinity of e to the x equals 0. So the limit as x goes to infinity of e to the x is infinity. The limit as x goes to negative infinity of e to the x is negative infinity. Is 0. The limit of natural log of x as x goes to infinity is infinity. The limit as x goes to 0 from the positive side of the natural log of x is negative infinity. The limit as x goes to infinity of e to the x is e to the x. The limit as x goes to infinity of e to the x is infinity. The limit as x goes to negative infinity of e to the x equals 0. Okay, so the limit as x goes to some power r, and r is even, is going to be infinity. So the limit going to plus or minus infinity of x raised to some power, and that power is even, it's going to be infinity. Barring that there's not a negative in front of it, that would flip this function over. So the limit of x goes to some power is infinity. The limit as x goes to some power as x approaches negative infinity equals negative infinity if r is odd. The limit as x goes to infinity of x raised to the r equals infinity. The limit as x goes to negative infinity from x raised to the r equals negative infinity if r is odd. Okay, a function has a saddle point, has both positive and negative values. A saddle point is a point that is not a local extreme, but it is also stationary. It gets its name from the resemblance of a surface near this point that looks like a saddle. Okay, so for a local minimum, basically a local minimum is the area on a graph. That's the lowest part, the area on a graph that's low, but a global or max minimum is the area on the graph that's furthest down. Same thing with local maximums. If you take and look at the function, you're looking for an area that's going up, it's positive, to turn from positive to negative. That'll be a local maximum, but then to find the global, you look for the highest area, and that will be your global. So for a function of a single variable, we define critical points as the values of the variable at which the function's derivative is equals 0 or does not exist. For functions of two or more variables, the concept is the same. So we're looking basically critical points. To find that, we take the derivative and we set it to 0 and solve. And if it's 0, then we know that's a critical number. So it's places where it's crossing 0. A function consists of all set of inputs and a set of outputs, and a rule for assigning each input with exactly one output. The set of inputs is the domain, and the set of outputs is the range. Set of outputs, excuse me. There are 4 possible ways to represent a function. You can represent it verbally by describing it in words. You can make a table of values that can describe what a function is doing. You can do it by a graph. And also you can just do it algebraically. The area of a circle is area equals pi r squared. The area of a square is area equals s squared. Slope-intercept form, y equals mx plus b. The general equation for a quadratic is ax squared plus bx plus c. So different function notation. So y equals, here the function. So instead of saying y equals this function, you could say y equals f of x is another way of describing that. So here we have the function again. Okay, so here we have the function again. We have the output of the y, which is y, and it equals some function, or f of x. And the x is still the same there inside the f of x. So it said y equals this function. So whenever we're given a graph, we want to be able to provide an equation of the function. The point slope form of a line equation is y minus y1 equals mx minus x1. So it shows here. So the value of y given in the point goes here. And then the value of x given in the point goes here. And then m is when you find two other points, or another point. And then that's how you can use this. So here's an example. F of x equals 3x plus 1. So the name of the function is f of x. The value for the input is x. And so when we plug values in x, we get the output. Okay, finding the max and minimum values by looking at the graph. Well, we can see there's going to be a max at x equals -4. And then there's another local max at 1, x equals 1. And then there's another minimum at x equals 3. Okay, all local max and min values refers to the y values. All values of f that have a local max or min refers to the x values. I put this on here because this is always on a word problem. So all local max and min values refers to y values. All values of f that have local max and min refers to all x values. Okay, so the absolute maximum of the graph is the greatest x coordinate of any point on the graph. Excuse me, the greatest y coordinate. The absolute minimum of f is the least y coordinate on the graph. Vertical asymptotes come in the form of x equals a. And when the value of a is plugged in, you get a vertical asymptote. So if x was 3, you'd go over to 3, and then it'd be a vertical line. If the y coordinates approach infinity, then the function will not have an absolute maximum. If the y coordinates approach negative infinity, then the function will not have an absolute maximum. A hole in the graph is an open circle. A hole is a point that is not on the graph, basically. If the hole of the graph has a greater y coordinate than any other point, then the function does not have an absolute max. The domain and range of y equals square root x plus 5. So I'm going to set what's in the root. X plus 5 is greater than or equal to 0. And then when we solve it, x is greater than or equal to negative 5. So negative 5 is a value that if I plug in, I'll get y equals 0. But if I go past negative 5 and plug in negative 6, then it won't be defined anymore. Find the domain. Okay, so we just did that one. Finding the domain range of y equals square root of negative x plus 6. Okay, so we solve it and we get x is less than or equal to 6. So the domain is going to be negative infinity to 6. And the range is going to be y equals 0. The domain of the square root of negative x, and then outside plus 9. So if I move the 9 across, that's going to give me negative x is greater than or equal to negative 9. And then when I solve, it's going to be x is less than or equal to negative 9. Okay, so if the derivative f prime changes from positive to negative, then there's going to be a local max. Like if I'm going up on a parabola, it's positive, 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 then it switches to negative, and that's a local max. And if the derivative changes from negative to positive, then you're going to have a local minimum. this with a smiley face. If the second derivative is greater than 0, then the function at that point is going to be concave up. If the second derivative is less than 0, then the graph will be concave down. To multiply polynomials, we use the distributive property. Unlike adding and subtracting polynomials, where you can only subtract and add things that are alike, here you can multiply everything using the distributive property. And the basic rule for multiplying and dividing exponents. Right. Yeah. Descartes' rule of signs to determine how many positive and how many negative real signs there are. Okay, go back to that one. To subtract polynomials. With polynomials, you can only add or subtract things that are alike. Unlike multiplying and dividing polynomials, where you can use the product and the quotient rule with exponents. When you're subtracting polynomials, you have to worry about the negative sign that's between these two right here. So this would become negative 2x squared plus 5x plus 12. And then once you do that, you can combine things that are alike. You have the 4x squares and you have the negative 2x squares, which gives you 2x squares, and so on. The leading coefficient test says that if a, or the leading number, is greater than 0, it's going to be positive. Graphs of polynomial functions. You have the, y equals 0 line. You have the linear function, which is just a degree of one polynomial. A quadratic function. A degree of two polynomials. A cube is a degree of 3. A quartic and a quintic, 4 and 5. So for a degree 2, there's going to be a 1 bump. Or x squared. That makes sense, a parabola. For degree 3, you're going to have just a graph of y equals x cubed. And then another degree 3, depending on how it is, you could have 2 bumps. And a degree 4, is following that even ideally, so degree 2 or x squared is a parabola. So the degree 4 is going to be some sort of parabola. It may not look the same. It could have one flattened bump, like the parabola, or it could have 3 bumps. Polynomials and radical functions. Two important features of a polynomial is that they're smooth and continuous. Here, as we notice, we go up and down. There's no jagged edges. Smooth and round quarter goes around. So polynomials are smooth and they're continuous. Something you could draw without lifting a pencil from the rectangular coordinate system. End behavior of a polynomial. On the leading coefficient test, it says that if x increases or decreases without bound, the graph of the polynomial is going to look so. So when it's odd, the leading coefficient is, if A is odd, whatever that number is, the leading coefficient is positive. The graph falls to the left and rises to the right. If the leading coefficient is negative, then the graph rises to the left and falls to the right. Smooth continuous graphs, we did that. Okay, so graphing a polynomial function. Use leading coefficient test to determine the end behavior, where the graph is going to infinity. To find the x-intercepts, you set the function as 0, and in the result, you'll have your x-intercepts. Okay, if k is even, the graph touches the x-axis and turns around. If it's odd, the graph crosses the x-axis at r. To find the y-intercept, we set plug in 0 for x and find the y-intercept. Okay, here's an example of using the leading coefficient test to determine the end behavior of the graph. Using the quadratic function y equals x cubed plus 3x squared minus x minus 3. Okay, so because the degree is odd and the leading coefficient is 1, the graph falls to the left and rises to the right. So since the leading coefficient was odd and positive, the graph falls to the left and then falls to the right and rises to the right. Finding the zeros of a polynomial. There's a lot of ways to find the zeros of a polynomial. One, we set the polynomial equal to 0 and solve. One, we factor the polynomial and then solve. You could use the quadratic equation and so on. Multiplicity and x-intercepts. Okay, so if r is 0 of even multiplicity, then the graph touches the x-axis, turns around at r. If r is 0 of the, just crop that one, turning points. Turning points are basically max and mins, and it turns from decreasing or increasing and decreasing. In this graph, x to the 5th minus 6x cubed plus 8x plus 1. This graph has 4 smooth turning points. Each of the turning points changes the graph from the direction of increasing and decreasing or vice versa. In calculus, these points are called local maximum or local minimum. Okay, so graphing a polynomial, here we're given x to the 4th minus 2x squared plus 1. Because the degree, the 4, and the x4th is even, and the leading coefficient is 1, it's going to rise to the left, rise to the right. So here's the graph again. Rises to the left and rises to the right. Okay, so for possible symmetry to help draw the graph or partial graph, suggests that we use that we have y-axis symmetry. Vertical translation. A function of the form y equals c plus a sine bx, or y equals c plus a cosine bx is shifted vertically when compared with the graph a sine x or a cosine x, so that y equals c plus a sine bx. That c is what raises that graph up. It could be a 5. I mean, if that c was 5, it would be raised up 5 on the graph. Phase shift. A function y equals sine x plus d has the shape of the basic sine graph, y equals sine x, but with a translation of d units. So what that basically means, to find that, if I have the x plus d, I would set that to equal to 0, and it would tell me what the phase shift is, how much I'm going to the right or going to the left. Okay, to the right, if d is less than 0, and to the left, if d is greater than 0. So the number d is just the phase shift of the graph. Whether it's cosine and sine, they both share the same traits. Just like a vertical translation, y equals c plus a sine bx or a cosine bx, that c out in the front, positive or negative, determines what's going to happen. The period of sine and cosine. The graph of y equals sine bx will look like that of sine x, but with a period of 2 pi divided by b. Okay, so I take either y equals sine bx or y equals cosine bx, and I take 2 pi divided by whatever b is, and that'll give us the period. So the period is 2 pi over b. In the previous chapters, you learned that the graph y equals f x minus h plus k. And if we look at that, y equals a times f x minus h plus k. So remember, the a is going to depend on what value it is. It's either going to shrink it, stretch it, and the x minus h, that's going to tell us our phase shift, and the k is going to be our vertical phase shift. If there's a 5 or so, whatever. So if I had to obtain the graph of y equals a sine bx, a sine b, x minus h plus k, transform the graph. Okay, let's see if they're showing an example. Okay, here we go. So vertical shift. I have the a sine bx plus k, and that's that k value that lifts it up or brings it down. And then down below I have a sine bx, where a is just another value. Okay, so horizontal shifts. Shifts the graph h units vertically. So the horizontal h inside, it's going to shift the graph to the left or to the right. Reflection. If a is less than 0, reflect the graph of the line over y equals k. Now remember, y equals k is just a general horizontal line after any vertical and horizontal shifts have been performed. So that a, you're basically taking a graph just like x squared. If I had an x squared and I had negative x squared, it's just going to flip the graph over. if I had negative and then x squared, not x squared multiplied 2. The graph y equals negative 2 plus 3 sine x to the fourth. So we know the negative 2 is going to shift it down. We know the 3 is going to, push the graph up or down, stretch it, and then finally whatever's inside, we can find the period by doing 2 pi. Okay, so because the transformation of the graph, y equals 3 sine 4x, the amplitude is going to be 3. And the period is, if I do 2 pi divided by b, because 4 is b, I get pi over 2. Therefore, it translates the graph down 2 units.